We've covered most of the fundamental principles that I wanted to get to in classical mechanics. We covered the idea of the Lagrangian and the idea of the action, which is the integral of the Lagrangian, and the fact that the action is minimized. And the action is going to come back when we talk about quantum mechanics. It's going to come back when we talk about special relativity. And it's also going to come back when we start talking about times when we have relativistic quantum mechanics and deeper fundamental physical principles. We talked about the definition of momentum in terms of the Lagrangian. We also introduced the Hamiltonian as a method of getting a more explicit version of the time evolution of a system. We also talked about the fundamental and very important relationship between symmetries of the Lagrangian and conserved quantities. Now, symmetry is a very important principle through all of physics, and the relationship between symmetry and conserved quantities is actually one that holds up through quantum mechanics and relativity, and indeed general relativity. Noether was brought in to try and help deal with the rather tricky problems associated with conserved quantities and general relativity, and that was the approach that succeeded in the end. In this lecture, we're going to come back to looking at classical mechanics systems. We're not going to look at how to set them up or how to generate the equations of motion. What we're going to look at is how to solve those equations of motion. And furthermore, how to then go and interpret what's going to happen. And so to really understand what a dynamical system does, we need to have some tools at our disposal. We're going to discuss that today. But just before I do, I want to talk to you about Poisson brackets. Suppose you have a function of your dynamical variables in a system, and you have another function of your dynamical variables in a system. This could be anything. This could be just one of the dynamical variables, or it could be some complicated function of them. Then the Poisson bracket of those two functions, which is written this way, is just a definition. It's defined as that. It is very easy and indeed assignment worthy to show this and this and this, where this is the Hamiltonian. And the reason we bring up Poisson brackets is that these relationships are very, very similar to equivalent relationships in quantum mechanics. And so these are often used as a kind of correspondence principle.